The last human footprints on the moon were pressed into the dust in 1972. For 54 years, those tracks have sat undisturbed in the vacuum, marking the final moments of a deep space presence that remained vacant for over half a century. That pause ended with a shockwave on the Florida coast. The Space Launch System, the only rocket currently capable of sending a crewed spacecraft directly to the moon in a single launch, thundered off the pad, carrying the Artemis II mission into orbit. Aboard were Commander Reed Weisman, pilot Victor Glover, and mission specialist Christina Coch and Jeremy Hansen. They were tasked with executing the first crewed flight to the lunar vicinity since the end of the Apollo program. Their vehicle, the Orion capsule, is a drastic departure from the cramped analog command modules of the 20th century. Driven by advanced digital flight systems, flat-screen interfaces, and state-of-the-art life support, it is built for long-duration operations. While the flight path of Artemis II traces a familiar loop around the moon, this is a highly calculated reconnaissance mission designed to test the hardware required to establish a permanent human presence at the lunar South Pole. Building a base on the moon means surviving a highly hostile environment. Without an atmosphere to burn up debris, the lunar surface is constantly bombarded by hypervelocity micrometeoroids, traveling thousands of miles per hour. Engineers call this specific threat impact flux. To build structures that won't depressurize, they have to calculate exactly how often and with how much kinetic energy a specific area of the moon is going to get hit. These localized strike frequencies dictate the physical blueprints of any future base. The data directly determines habitat wall thickness, materials used, and how much redundant shielding is required to keep an outpost safe. Automated orbital sensors have tracked large impacts for years, but smaller, highly dangerous strikes are difficult to measure from a distance using automated instruments alone. To confidently design the Artemis base camp, researchers needed to calibrate their mathematical models. They needed highly trained human observers on site to witness and record these rapid, violent events in real time. On Flight Day 6, the Orion spacecraft reached the climax of its outbound journey, slipping over the horizon toward the massive, heavily cratered far side of the moon. Without relay satellites behind the moon, orbital mechanics create a strict communications dead zone. The moon's physical mass entirely blocks the line of sight to Earth. For 40 minutes, the crew was cut off. No radio, telemetry, or live support from mission control. They spent this time executing the Lunar Targeting Plan, a tightly choreographed set of observational assignments designed specifically for the unique lighting conditions of the lunar far side. Orion was equipped with an array of 31 state-of-the-art cameras, all configured to capture high-resolution imagery and video in an environment largely devoid of sunlight. But as they stared down into the pitch-black void of the lunar surface, the most valuable scientific instrument turned out to be the astronauts themselves. Looking out the windows of the capsule, the crew scanned a rugged terrain illuminated by nothing more than the faint reflection of starlight. Without the aid of any optical equipment, they reported seeing 6 distinct, rapid flashes of light flickering across the darkened surface below. These flashes were the exact data points NASA was looking for, the violent sparks of meteoroids vaporizing as they slammed directly into the lunar dust at extreme kinetic speeds. Digital cameras, even highly advanced ones, struggle to capture these events. The extreme contrast between the absolute black background and the split-second pinpoint flicker of a strike easily overwhelms the sensor's dynamic range. The human eye and brain, however, are evolutionarily optimized for exactly this scenario. Our visual cortex is highly sensitive to faint light contrast and sudden rapid movement in extreme low-light environments. If the crew had simply relied on automated instruments, the strikes would have been lost in the digital noise. By actively observing the surface, they secured hard evidence of the lunar impact rate. As Orion emerged from the lunar shadow and communications were restored, the crew beamed back a view of a crescent Earth rising over the heavily cratered horizon. They also beamed back telemetry confirming a major milestone. The spacecraft had pushed roughly 4,600 miles past the moon, breaking the long-standing human distance record set by the Apollo 13 crew in 1970. Reaching over 252,000 miles from Earth was a calculated trajectory choice. That high-altitude flyby gave the astronauts an incredibly wide-field vantage point of the entire lunar environment. Back on Earth, researchers and citizen scientists immediately began cross-referencing the crew's visual reports with orbital data to map the exact locations of the 6 flashes. By analyzing the timing and brightness of those specific strikes, physicists can accurately calculate the size, mass, and kinetic energy of the impactors that caused them. This real-world data feeds directly into the engineering models for the Artemis base camp. It confirmed that current shielding technology is fully capable of suppressing micrometeoroid hazards, reducing the physical risk to a manageable level. By documenting these strikes with their own eyes, the astronauts secured the specific environmental variables required to keep future explorers alive. Artemis II provided the hard data that makes the lunar South Pole a survivable destination.